to Unit 6, Video 5, Radioactive Decay. By the end of this video, you should understand why atoms undergo radioactive decay. You should know the types of radioactive decay. You should be able to complete decay equations for alpha, beta, and gamma decay. And you should know what half-life is and how to perform calculations using the concept of half-life. Before we begin, it's important to realize how radioactive decay is different from the processes we'll be looking at for the rest of the year. We'll be looking at chemical processes all year, but radioactive decay is a nuclear process, meaning it's a reaction that changes the composition of an atom's nucleus. Since we're changing the composition of the nucleus, we'll be changing the number of protons in many cases, and therefore we'll be changing what the element is, because remember, the number of protons determine what element we have. So you might have at this point asked yourself, why don't the protons in the nucleus repel each other? Recall that we have established that the nucleus is a very dense ball of packed protons very close together, which doesn't seem to make sense since we already know that protons are positively charged. It seems sensible that they should just repel each other. The answer is the strong nuclear force, which is the attractive force between protons and neutrons that holds the nucleus together. This force is strong enough to overcome the repulsion between protons. So even though the protons are repelling, the strong nuclear force is holding them together. When you have more neutrons in a nucleus, you have more strong nuclear force. But since neutrons don't actually carry any charge, you also do not add any repulsion. So generally speaking, more neutrons will give more stability, to a certain point though. First, it's important to remember that most atoms are stable. There aren't that many nuclei that are unstable, for obvious reasons. If it's unstable, it likely has already decayed. So naturally, there aren't that many unstable elements in nature. Stability depends on the ratio between protons and neutrons in the nucleus. Too many or too few neutrons can make an atom unstable. Here we're looking at a graph of number of neutrons versus number of protons. Essentially, we've graphed the ratio of protons to neutrons. Nuclei with a ratio represented by a blue dot are generally stable. This represents an ideal ratio between protons and neutrons. Nuclei that have a ratio above or below this belt of stability will have to undergo some kind of radioactive decay to change the ratio of protons to neutrons. This will result in a more stable nucleus. So, radioactive decay is defined as the spontaneous breakdown of an unstable nucleus. This spontaneous part is important. This is not a man-made process. Radioactive decay happens spontaneously and naturally. The three types we're going to look at are alpha decay, beta decay, and gamma decay. So what do you need to know about these three types of radioactive decay? First, the symbol. Alpha decay and beta decay and gamma decay can each be represented by the Greek letter alpha, beta, or gamma. We can also represent alpha decay as 4,2 alpha or 4,2 helium, 4 being the mass number and 2 being the atomic number. Notice that alpha particles have a mass of 4, whereas beta particles have essentially no mass that's a negligible mass, and gamma rays have actually no mass. Gamma rays are actually not particles at all, they're really just energy. So why does alpha decay occur? Well, alpha decay occurs when there's too many protons in the nucleus for the nucleus to be stable. So very heavy elements, elements with large nuclei, will undergo alpha decay. Here's an example. We're starting with an atom of americinium-241. It will emit an alpha particle to give us neptunium-237. Recall that an alpha particle has 2 protons and 2 neutrons. Therefore, when it emits an alpha particle, its mass number will decrease by 4, because 2 and 2 is 4, and its atomic number will decrease by 2. Beta decay occurs when there are too many neutrons in the nucleus. Because there are too many neutrons, a neutron will be converted into an electron and a proton. The electron gets emitted, but the proton remains. So here we have a hydrogen nucleus. This is a tritium nucleus because it has a mass number of 3. One of its neutrons will be converted to a proton and an electron. The electron will leave, and the element now has 2 protons, making it helium instead of hydrogen. Gamma decay occurs when there's too much energy in the nucleus. This does not cause a change to the structure of the nucleus, nor does it cause a change to the element. Here we see we started with helium-3, and a photon of energy, which is essentially a little packet of energy, is emitted. And we still have helium-3 because we haven't changed the number of protons or neutrons. We can represent these nuclear processes by writing nuclear decay equations. Again, the mass number and the atomic number must be equal for reactants and products, meaning we can't create or destroy any mass. The resulting element after the decay is determined by the number of protons, or the atomic number. So for instance, here's an alpha decay equation. Notice we've started with a uranium-238 nucleus. It has emitted an alpha particle, or a helium nucleus, which has caused its mass number to decrease by 4 and its atomic number to decrease by 2. Also notice we've conserved mass. 234 plus 4 gives us 238, and 90 plus 2 gives us 92. Here's an example of a beta decay equation. Here we have a carbon-14 nucleus. It emits a beta particle which has no mass and essentially changes our mass number by adding 1, because recall the proton stays but the electron leaves. Again, 14 and 0 is 14, and 7 and negative 1 is 6. And finally, gamma decay we can just represent by adding a gamma symbol at the end, since we're not changing the nucleus. This dot here represents an excited iodine nucleus, meaning it has too much energy. Just to get some terminology straight, we often refer to the atom before decay as the parent atom, and the atom produced after the decay as the daughter atom. Here's some to try on your own. Pause the video here and try to fill in the blanks. When you return, I'll display the answers. Welcome back. Here's what you should have gotten. If you chose to use a different symbol for the beta particle and the alpha particle, that's fine. You can do them any of the ways you saw on the chart a few slides back. Also, it's important to notice that some of these have decayed into another nucleus that is also unstable. For instance, here, the decay product, uranium-235, is still slightly unstable. It can then decay again from there to create another stable nucleus. In terms of time, we can use the idea of half-life to quantify the amount of time it takes for half of a sample of a given radioactive element to decay. So for instance, here's some half-lives of some common isotopes. It takes 8.1 days for a sample of iodine-131 to decay by half. In other words, if I start out with 100 iodine-131 nuclei, after 8.1 days, half of that will be gone. I'll be left with 50 iodine-131 nuclei, and the other 50 will have decayed. After another 8.1 days, so 16.2 days in total, that sample will cut in half again to 25 nuclei of iodine-131. After another 8.1 days, that 25 will cut in half again to 12.5, and so on and so forth. Notice there's a wide range of half-lives. Uranium-238, for instance, has an incredibly long half-life, which makes it very difficult to store and to dispose of. You may have heard of carbon-14. This is the nucleus used in carbon dating. This also has a very long half-life, 5,700 years in fact. This is the ratio of carbon-14 to carbon-12 in a substance can actually give us a sense of how old the substance is based on the half-life. Here's a visual representation of half-life. Imagine I start with 16 grams of radioactive lead. Each gram here is represented by a cube. The half-life of radioactive lead, lead-210, is 22 years. So after 22 years, half of that sample will remain undecayed. After 44 years, another half of that sample will decay, so we'll be left with a quarter of the original sample. After another 22 years, 66 years in total, we'll be left with an eighth of the original sample because another half will have decayed. Eventually, it will decay down to nothing. We can also represent exponential decay graphically using an exponential trend line to fit our data. Here we started with 10 grams of radioactive carbon-14. After one half-life, or 5,730 years, we're left with 5 grams of our original 10-gram sample. After another 5,730 years, we're left with 2.5 grams, or half of our 5-gram sample, and so on and so forth. This will continue, and even though an exponential decay graph never reaches zero, there will come a point where the very last atom will decay. We just can't predict exactly when that will happen. The best fit line for this data will take the following form. It's not a y equals mx plus b equation since it's not a linear line. A is the mass of the original sample, so in this case that would be 10 grams. E to the negative bx is equal to the half-life, so in this case that will be 5,730 years. That brings us to the end of this video. Let's review our goals. First, we looked at why atoms undergo radioactive decay. Recall that's to gain a more stable nucleus or a better ratio between protons and neutrons. Then we looked at the types of radioactive decay, alpha, beta, and gamma decay. Then we learned how to complete decay equations for alpha, beta, and gamma decay. And finally, we looked at half-life and how to perform calculations using half-life.